All right, taking a look at a video this time that deals with another tool in the proving toolbox. How do we go about proving particular things dealing with shapes? This deals most specifically a lot of times with quadrilaterals, also deal with triangles a little bit as well, but it's another way to go about doing things. Sometimes this is faster and easier, but at the same time it also has a limited set of things that it's able to do that we'll go through here. First, we'll take a look at the formula reminders. What are the formulas we use in coordinate geometry? There's 3 of them. And it's placing shapes. How do you put a shape down so that you can use coordinate geometry in order to prove it? And we'll look at an example using slope, an example using distance, and an example using midpoints. Right, so the first thing has to do with 3 formulas that we can use: the distance formula, the slope formula, and the midpoint formula. These are things that you should have worked with prior to getting to this particular lesson. The distance formula is useful for pretty much for just proving anything that you want to have about distances. You might be able to say distances are equal. You might be able to say things like distances are half as big or 3 times as big, or whatever the case is. It just deals with how long is one side compared to another. Usually we're dealing with this distance is the same as that distance. So this would be the segments are the same length, the sides are the same length, or some other thing happens to be the same size. Slope is used for 2 main purposes. It's used to prove things are parallel, and it's used to prove things are perpendicular. So when you calculate the slope, if you have 2 slopes that are the same, that shows that whatever it is that you're trying to work with has to be parallel. And if you end up with slopes that are opposite reciprocals, then that shows that they have to be perpendicular. I'll try to hit an example that hits both of those. Very simple, easy process on what it is that's happening there. All right. Last piece is the midpoint. Midpoint is really only useful for a couple of things. It's good for proving things are half as big as some other things, or finding out where the midpoint is if that happens to be necessary. It can also be used with the concept of a bisector to show that something mid spot or midpoint or place in the middle, or the bisector spot happens to be in a particular location. So those are your 3 things. That's pretty much all they do. You can only deal with distances, parallel and perpendicular. You can also show not parallel by showing the slopes aren't the same. So there's some things you can do with that as well. And then the midpoint has a lot of limited uses, mostly boiling down to the concept or the idea of bisectors. The first concept you got to worry about when you're dealing with coordinate proof is how do you place your shapes. So there's a couple things that you want to have to be able to follow there. The first one's a suggestion. It doesn't really have to be a have to. You want zeros. I'll show you why in just a second. That makes sense because it makes the formulas easier. Anytime you're multiplying, adding, or subtracting with a 0, it doesn't do anything. And the multiplication just makes it easy. In this case, we're doing a lot of adding and subtracting. You want zeros. So when you go to place your shape on here, you want to be able to create as many zeros as you can. The second thing you have to worry about when you're placing your shapes is that you have to follow what the shape is. So you have to create the shape on your little grid so that it's what the shape is supposed to be. It follows the properties of what that shape is. Third thing that you need to worry about here, and this is a must, you must have as few variables as possible. Now this is what confuses some students here. Like, what are you talking about variables? Well, when I go to put a square, say for example, on the coordinate plane, I can't say it's 5 units here and 5 units here, because that's not a proof for all squares. It'll only be a proof for a square that's 5 by 5 by 5 by 5. So you have to use variables and letters when it is that you're placing your shapes that's on there. And that's what's confusing to students. But the key is, it's just what's the shape? And then once you know what the shape is, place it on the plane. Once you know what it is on the plane, then you just use the correct formula to show whatever it is that you happen to be showing. So let's just show a few shapes. I'm not going to get to absolutely everything. So let's take a look first of all at an easy shape. A shape is a square. Square, I know in my head, means that you have a 90-degree angle. You can assume the x and y axis make a 90-degree angle, so that's good. Got a right angle there. And I know all the sides are the same. So the coordinates of this corner are 0, 0. That's really helpful because I can now use zeros when I go to start calculating my formula. Zeros are really useful. This point out here is the point A0. A units. I don't know exactly how long it is. It could be 5, could be 5,000. It doesn't really matter what it is. Whatever A is, that's how far out it is there. Well, since this is a square, if it's A that way, then it's A this way. So this point up here is 0A, and the coordinates of this point would be AA. And now I can use my formulas on that. We'll show an example here in a couple minutes on how it is that you go about doing that. But that's now a square that's in the Cartesian plane, and I can now calculate like the diagonal's length or the other diagonal's length, or I can calculate slopes. And if for whatever reason I need to find a midpoint, I can calculate the midpoint just based on those letters that are there. Don't let the letters confuse you, because they're not terrible. All right, let's try a rectangle next. That's a nice easy one for a lot of students. Again, I put the corner down here. I want as many zeros as I can get. I don't have to use zeros, but they sure make life easier. Try to put things on the axes or even in the corner down here if you can. All right, so this is a rectangle. So again, I'm going to say it's A0. That means it's A units out here. 0 means there is no up and down, meaning it's sitting right on the axis. That introduces another 0. Now this, unlike a square, isn't the same length. So if that's A, maybe this is 0B. I don't know how big exactly B is, but this is B units above here, and it's not the same as the A that's there. And then this coordinate here, because this is a rectangle, it's even this way and even that way, so this would be the coordinates AB. So those would be a rectangle in the Cartesian plane there. All right. Let's try something else easy. Let's try just a plain old triangle. Well, a triangle has no special properties about it, so I'm just going to place it in here. I know still that this corner is at 0, 0. I have no idea how far over that one is. I just know it's over there. And then this isn't necessarily in the middle, so we might call this spot up here BC. B meaning I don't know how far over I had to go, and I don't know how far I had to go up, so nothing is set. It's just a plain old triangle with 3 side lengths based on what A, B, and C happen to turn out to be. Well, maybe I want something more specific. Maybe I want an isosceles triangle. Well, an isosceles triangle is even in the middle, so that'd be nice. This is the first time we'll have done one of these, but I can just go in both sides. I know I'm even in the middle, so even though I didn't use 0, 0 this time, I have some easy things I can do. From here over to there is A0. Whatever distance that is, it's even distance this way, so we would call it the opposite of A0. So if this is 3 units, this is -3. If this is 10, this is -10. If this is 4,055, this is -4,055. It's just the same distance in both directions, making the triangle isosceles. I don't know how tall up it is, but I still have another 0. Still ended up with 3 zeros by placing it strategically. Do you have to place an isosceles triangle just like that? No, you don't. There's some other different ways you can do that, but that's an easy one that a lot of students can go with. All right, so let's say something like this. Let's say we have a trapezoid, okay? So start placing my trapezoid. This is not an isosceles trapezoid, so we got to make it a little bit longer there. So I just go through my corners. I just know these 2 sides are parallel because that's what makes it a trapezoid. That's fine. So this corner is at 0, 0. This corner way over here, don't know how far over it is, so we just call it A0. Okay. This one, I don't know how far over this is, so it's B units over, we'll call it C units up. See, I'm having to come with a now, and this last one's going to matter because this has to be the same height because it's parallel. These 2 sides are parallel, so I might call this one DC. Notice how the C's match. That means they're at the same height. So it's important for you to understand a little bit about what's going on with the Cartesian plane and what the coordinates mean and matter. That's something you should have done before you got to this video to begin with. All right, what else can we put on here? Let's try an isosceles trapezoid. Isosceles trapezoid is even on 2 sides. So maybe I split it down the middle like I did on my isosceles triangle. Didn't use 0, 0, but I'll still have plenty of them. This point over here is A0. Since this is isosceles, however far that was, this is backwards. Now this spot is BC. And this spot would be the opposite of BC. The C's are the same because they're the same height up off the y-axis. The opposite of B's is because whatever distance this is the distance in the opposite direction. So that would be an isosceles trapezoid. We'll call it isoid. This one down here was just a trapezoid. Parallelogram. Just need parallel. I'll use those properties. This one's kind of funny. That's a really terrible drawing of that, and I'm sorry. But I have 0, 0 here. I have A, 0 there, meaning that distance from here to there is A. This spot up here will be BC. I don't know how far over or exactly how far up. This last one, because these sides have to be parallel, just like it was on the trapezoid, that'll be a C. But this one can't be D this time, because I actually can tell you about how far over that is. I go B distance this way, plus since these two sides are the same, A distance all the way over there. So from here, which is what the x-coordinate measures, is from the axis over. From that axis over, in this case, is A plus B. Okay? Equilateral triangle is actually really hard to draw, so I'm not going to do one of those. A kite or a rhombus, I'll just do one more, but these are more or less the same thing. Now let's just do kite, since a kite's not necessarily the same. Longer side there. Again, I didn't use the origin, but then just follow your same rules. The kite is a nice even shape. So if this is A0 on this side, this is the opposite of A0 on that side, because it's even on those two sides. Not even this way, but it is even that way. This point here might be 0B. And since this is not the same distance down, this would have to be 0C, or 0 the opposite of C, if you prefer to do that as well. Right? So all I'm doing here is taking the shapes, sticking them on the coordinate plane, and then just using letters for how far it is or over that I need to go. Now some students are like, well, I don't get this letter thing. Well, that's fine. Take your coordinate plane, let's say I'm going to use a rectangle, and begin to invent your rectangle. This is still 0, 0 no matter what. This is 5, 0. Now I put a number in there, but I'll take it out in just a second. So I know that the rectangle, I don't know how far over that is. Maybe this is 0, 3, and that's 5, 3 there. You can go back through and replace the same numbers with a letter that goes with it as well. So don't let this be a horribly confusing process. All right, so now I want to take a look at using slope. How do I use slope to be able to prove something? So let's show you two things here. Let's take a square, just for ease. And we're going to show two things. First thing we're going to show is that the top and bottom are parallel. And the second thing we'll show is that the diagonals are perpendicular. So I'm going to have to do a little calculating here, but it's not a big deal. So the first thing I do is, that's where I'm headed, I've got a square. So I need a square on my plane here. So this is 0, 0, A, 0, 0, A. Since it's a square, it's the same in both of those directions, which makes this point AA. Right? And since I'm trying to show parallel, I know that tells me that I need to use slope, so I need to calculate some slopes. In this case, I'm trying to show that the top and the bottom have the same slope. Okay? Well, the slope formula for the top and the bottom, so we'll say slope of the top, or if this was a segment like AB, I could say slope of segment AB. The slope of the top is y minus y, which is A minus A, over x minus x, which is 0 minus A. That's 0 over the opposite of A. Just because that's an A there shouldn't confuse you. If you have no dollars and want to divide it out into A pieces, you end up with 0. That shouldn't be a big deal. Your calculator should be able to tell you that. The slope of the bottom, y minus y is 0 minus 0. X minus x is A minus 0. That's 0 over A, which is 0. Since those two numbers match, I've just proven that they're parallel. That's what that does. That's well, and look how quick and easy of, quote unquote, easy of a proof it is. If you know how to get the shape on there, you know what shape it is you're dealing with, and if you can get your letters in there correctly, everything else now just becomes a process of plugging in the values that are there. Sure, the diagonals are perpendicular, a little bit different calculation. So that's diagonal is here, the other diagonal is there. Let's calculate the slopes. Let's give these some letters this time. A, B, C, D. So we want the slope of segment AC. Y minus Y is A minus 0. X minus X is A minus 0, which is A over A, which is 1. So the slope of that line is 1. Slope of the other one, slope of BD, is Y minus Y, which is A minus 0, over X minus X, which is 0 minus A. That's A over the opposite of A, which is negative 1. Now, unlike parallel, where I'm looking for them to be the same number, what I'm looking for when they're perpendicular is that they're opposite reciprocals. So here's what that means. Opposite reciprocal means that you turn it into a fraction. Reciprocal means to turn it over. Well, 1 is technically 1 over 1. When you turn that over, it's still 1 over 1. It doesn't do anything. And then the word opposite means to change the sign. So if I take 1 over 1, turn it over and change the sign, the opposite of 1 over 1 is negative 1, which is exactly what that value is. So because 1 and the opposite of 1 are opposite reciprocals, I've just proven that they have to meet at a right angle. That's a property you should have learned in an early algebra course when dealing with graphing and that sort of thing. All right, so that's how you can do slope. Distance will be a little bit quicker. All right, here we go. So let's say I have a rectangle and I want to show the diagonals are the same. And the board is dragging things out a little bit. So there's a rectangle, 0, 0. I'm going to call this point A. Let's call this A0 as we have been doing. 0B. And this is AB. My diagonals are like that. A, B, C, D. So I want to show that AC is the same length as BD. So the distance from A to C is equal to the square root of, and this is the reason I'm doing this particular example, I just want to show you a few things as we get through there. So AC x minus x, so that's going to be A minus 0 squared, and Y minus Y, which is B minus 0 squared, which is the square root of A minus 0 is A squared is A squared, B minus 0 is B squared is B squared. A lot of students want to take this square root, don't. The sum, you're taking the square root of the sum, not the square root of each one of these things, so I have to know what the sum is before I can take the square root. So that's actually the end. So these are big, long, horrible, complicated formulas of variables and stuff like that. That's all it took was 2 steps. Plug in these values, plug in that value, work it out, and just leave it like that. All I'm looking for is a match. I don't have to simplify it down to something beautiful and wonderful. All I have to do is show that AC's calculation turns out to be the same as BD's calculation. So let's test and see if it is. BD, x minus x is 0 minus A squared. Y minus y is B minus 0 squared. So this is the square root of. 0 minus A is the opposite of A. Opposite of A times the opposite of A, which is what squaring means. Gets rid of the negative and turns it into A squared. B minus 0 is B. B squared is B squared. Look, there's a match. So segment AC's distance is the same as segment BC's distance, so the diagonals have to be the same length. Right? There are other ways to go about proving these things. You'll deal with, probably in a later lesson, I'm just dealing with the properties of coordinate proof, but you can use congruent triangles and some things like that. But sometimes it's just a nice, quick, easy way to be able to go through and do things if you understand how to do it. All right. Move on. There we go. Using midpoints. Let's do something different. Let's say we have a kite this time. And on the kite, I want to show that the diagonals do not have the same midpoint. Let's get us a kite first. Kite is an even shape in one direction, but not the other. So this is A0. The opposite of A0. That also gives me a chance to bring that negative in there to show you how that works. This is 0B. And then this is going to have to be 0C. Now, some students will ask why not make it negative C since it's down below there. That's fine, but it's a variable. The variable can be positive or negative, so it doesn't really matter what it is. So I'm just going to leave it as C there. So I want to show that they don't have the same midpoint. So we're going to calculate one midpoint, which is going to be easy, and then we'll calculate the other midpoint and show that they're not the same. So let's call this A, B, C, D. So the midpoint of segment BD, this one will be easy, is equal to x plus x, which is the opposite of a plus a over 2, and y plus y, 0 plus 0 over 2, that's a piece of cake. Opposite of a plus a is 0. 0 divided by 2 is 0. 0 plus 0 is 0. 0 divided by 2 is 0, so the midpoint of segment BD is at 0, 0, which should make sense since this is an even shape on those two sides. Now let's do the other two. The midpoint of segment AC is 0 plus 0 divided by 2, and B plus C divided by 2, well, that's ugly. 0 plus 0 is 0. 0 divided by 2 is 0. B plus C, I have no idea what that is because I don't know what B and C are. So this can't simplify. This just becomes, or stays, B plus C divided by 2. And if that's as far as I can go, these two are not the same. So I just proved what it was that I was trying to do, that they do not have the same midpoint. Another way you could say that is they don't bisect each other. This one is bisected because 0, 0 is right in the middle. This one's not bisected because I don't even know where B plus C is. I just know it's not at 0, 0, so they don't cut each other in half. All right, so you have direct proof, which has 3 different forms. You have indirect proof, which has an assumption that uses the law of contrapositive. Now you have one last way, tool in the toolbox, to try to be able to prove some different things. This is usually going to be used with your quadrilaterals. The key is getting the shape on there, getting as many zeros as you can, minimizing the number of variables, and then just performing the correct calculation. But you got to know what a shape is and what it kind of looks like in order to put it on there, and you got to know your formulas. So those are the 2 things that you got to be able to do on this video. If you need help placing your shapes, feel free to talk to your teacher. Be happy to help you out on what it is that you need to do to get the shape in the right place. And then got to know your formulas. You got to know how to use them and how to take the values out and plug them in to be able to simplify. But if you have any questions, make sure you talk to your teacher. Be happy to give you some help as you get through and start practicing this. Until next time, see ya.